Some people hear me? Hey, like, someone hear me? Okay, so but I do hear me, and that is a problem. I have no idea why. Or maybe because I hear the YouTube thing started. Again, let's try. I do not hear me, so it seems to be okay. Yeah, wondering like how many of you are following. So should we wait a couple of minutes more? Or... okay. Okay, so I think we'll start. So is that okay for everybody? Yeah, so something important. Okay, so something important. I will try to follow like the Discord. So yeah, so I will try to follow the Discord as much as I can. And so whenever there is a question, that it is very important to to say it. Okay, so thank you very much. Uh, Thank you very much for listening at me. So we're gonna to talk about artificial intelligence. That is a very good question. What is confident? What is default audio channel? Discord or YouTube? I have no idea. Maybe someone can help there. Yeah. Yeah, I think that the Discord is just for answering question, asking question, answering question, no more. Okay, so yeah, so the title is artificial intelligence, but actually we're going to talk mainly about neural networks. I know that artificial intelligence is much more than neural networks, but we're going to talk about that for today. So the goal of this talk is to show what can be done in plain Pharo related to neural network. So we will not use any external libraries or some web services. We will simply use some plain Pharo with nothing external to it. So here, this is a disclaimer for these slides. So what I'm going to show is a very condensed version of a lecture that I give at the University of Chile. Something important is that the talk is very incremental in its content. So if there is something that you do not understand, then just say it right away. Do not wait for later, because probably it will not happen that we'll understand. So neural networks involve a great deal of mathematical background. I try to remove as much as I can. So even you may see some weird formulas in the slides, but do not get afraid. I really try to distill all the theoretical content in something which is really practical. So you should not be afraid, whatsoever. And if you do not understand something, then it means that please ask. Do not, there is no dumb question. So just ask if there is something that you do not understand. So here, this is the Gopher script to load a bit of code that we're going to use at the end of the talk. But again, this is not a release, not yet. So how are we doing so far? Is it okay? Everybody can follow me? Yeah, people do hear me? Everything is okay? Just want to know before I start. Okay, so it looks okay. Yes, Danny, so it loads a lot of glamour packages, but I think this is due to, because the neural networks is loading Russell, and Russell is loading the whole GT thing, I guess. So yeah, okay. So now I will start. So here, this is what the talk, the structure of the talk. First, we're going to talk about the perceptron. The perceptron is it is a kind of artificial neuron. So we will first see how we can implement a perceptron. Then we will see how we can make this perceptron learn. And then we will see some limitation of the perceptron, which will motivate us to have a better way to have an artificial neuron, which is called the sigmoid neuron. So far we have been dealing with one single neuron. Then we will start to put neurons together in order to have the neural network. And then at the end, we will apply the neural networks to have to do some real job, which in that case will be about classifying some data. Okay, so let's start with the perceptron. So this is a neuron. So I'm not a biologist at all, but from what I understood from reading books from biology, then a neuron, this is something that everybody has in the brain. So in the brain there are plenty of neurons, and here we have one picture of one. So here the neuron gets some input, some electrical stimulus coming from the dendrites. Then you have here the body cell that is doing something with all these inputs coming, and then in some cases the neuron here may produce electrical impulses that is transmitted using the axon. So this this vision of neurons, we know it for long time, and having being able to create an artificial neuron has been the topic of computer scientists for many years. So there is this idea of having an artificial neuron since the 40s at least, and in the 50s and 60s, there were some guys, some very smart guys, thought about an artificial neuron called the perceptron. And the perceptron is something, is something that gets some input. In that case, here I have three inputs. and one output. So the perceptron can have 0, 1, 2, or many more inputs. Here I have 3, but I could have 10 or 20 or whatever. And I just have one output, one single output. And so the input and output are actually numbers. And so a perceptron accepts some values. So something that with the perceptron, in order for the perceptron to do something interesting, so it needs to give priorities to some input. So not here, like not all the inputs here have the same importance for doing the computation that the perceptron has to do. So how can we give importance to some input? By putting some weight, very easy. So the idea here, we have the perceptron that has 3 inputs, and for each input there is a weight also, which is a number. So everything here is a number. And the computation that the perceptron can do is the following. So here it will multiply x1 by w1, summed with x2 multiplied by w2, and summed with x3 multiplied by w3. This will give, so we multiply these two guys plus these two guys plus these two guys. And this will give a number. And if the number is above a threshold called t here, then the perceptron will produce 1. And if the value we computed here is below t, then we just produce 0. So that's the idea of the perceptron. So if we need to write it a bit mathematically, then this is how it is done. So yeah, so here the output is 0 if the weighted sum of the input is below the threshold, else is, it fires 1. So actually, if you don't understand that thing, doesn't matter. So now here I will explain like what the perceptron is useful for. So a perceptron is a kind of small machine to help to make decision by giving some weight to some inputs. So let's take a very simple example. So just check here just check. Some people, I see that some people are having some problem with loading, but it really doesn't matter. Actually, I provided the code, but maybe I shouldn't have not, because that is really not the point. I mean, I will just use one piece of code of that package, so really no stress if you cannot load it, because I will program everything myself. So, okay, so here we have the perceptron. We know I've shown a bit the model of the perceptron. So another question is what the perceptron is useful for. The perceptron is useful to make decision. So let's take a very simple example. So as I am sure that you have very good musical taste, let's imagine that you're a big hard metal music lover. So you love metal music, you're a big fan of metal music, and there is a concert this weekend, and you're wondering whether you should go or not to that concert. And like what makes you think about what makes you decide to go to the concert or not? There could be several factors. So here I have 3 factors. So you may want to go to the concert if the weather is good. If the weather is good, if there is no rain, then like that is a good reason for going to the concert. Or also, it may be that you want to go to the concert if someone can join you. It could be your brother, sister, or your boyfriend, girlfriend. If someone wants to accompany you, then that is a good reason to go to the concert. And or also, like if you are like me, if you do not like driving at all, then having the concert near a metro stop is also a very good, good reason for going to the concert. So here, it could have like many more factors, such as the price, such as the band that will play. But let's stick to 3 factors. So let's put a name to these factors. So here we will call this one x1, then the second one x2, and this third one here x3. So here we have 3 factors, and then we can start to make decision. So assume that if you are a very true metal lover that really like metal music, and you also like love to share the experience, the event. So in that case, you don't really care if the weather is bad, and you don't care, you don't mind really to walk, to the concert. So in that case, such a person will have the following weight. They will have W1 with a small weight, which is 2, and a higher weight for 6, and a small weight for 2. So in that case, someone with those weight means that we prioritize that thing here. So we prioritize that factors, and that factors, whether the weather is good or whether the concert is close to a metro stop, is not really important because they have small weight. What I mean by small and big weights doesn't really matter. It's just some 6 is greater than 2, so x2, the factor x2 has more importance than the other one. But you could have also different weight. You could have if you are willing to go to the concert, something that could be very important for you is to not wake up your parents to fetch you at the end of the concert. So in that case, for you, it could be very important to that the metro is close to metro. In that case, you don't mind whether the weather is good or not, and you don't mind whether to be alone. You are happy to go alone. But something very important is that the concert is close to a metro stop, and this is what these 3 here weights gives. And yeah. Okay, so now we can, here we have the factors and we have some weight, so we can start to make a decision. So to make the decision, X check, yes, there is sound. But I guess everybody listening to me, right? So is the problem that X check is saying only him or everybody? Yes, so that is the thing here. Okay, so I continue. So here, like the okay, so let's check here the YouTube. Yes. Yeah. Again, like if you have any question, just write it somewhere. Like just write it on the Discord or on the YouTube channel. That will be helpful. Really, this is very important that you understand every step here. Okay, so then we have seen how the perceptron works, and we have seen a small example with the concert. So we can have the following formulas where we have x1, the factor 1 multiplied by the weight 1, plus the x2 multiplied by weight 2 and x3 multiplied by weight 3. If the sum of this is above or equal to the threshold 5, then we say that the condition is true. And in that case, the perceptron will output 1. If this condition here is not true, then the perceptron will output 0. So why 5? Well, I mean, this is a threshold. I could pick any numbers, but this is just a threshold that I have arbitrarily taken. So let's talk a bit more about this threshold here. So here I have the 3 factors, and here I have some weight. So the threshold is important because the threshold, is really like the limit, above for the computation, really to tell you whether you go or not to the concert. So here I have, if I take the threshold 5, then you see that there are not many possibilities for you to go to the concert. It means that the only way for you to go to the concert is if the factor 2 is met, if someone wants to join you, because you have the weight 6 to that factors. It means that the only way for you to go to the concert if someone joins you. It means that if nobody joins you, but if the weather is good, and if the concert is close to a metro, this is not enough, because this will sum 4, and 4 is below 5. So the only chance for you to go to the concert is someone is joining you. So now if we reduce the threshold, if we, instead of having 5, if we have 2. So if with the threshold of 2, it is much easier for you to go to the concert. It means that, whatever the reason, we need at least one factor to be okay. So if the weather is good, then you know, if the weather is good, or if someone's joining you, or if you are close to a metro, then you will go. Any of these conditions here is enough to be equal to 2 or above 2. So we see here on this example that if we decrease the threshold, then it means that you are more willing to do to the metal party. Okay, so that is a perceptron, and that is what is useful for. So this is a bit of theory, but soon we will start to code, I promise. Okay, so before starting to code, actually, there is a small adaptation that I would like to make to the perceptron. So we have used the word threshold, but I want to change the word threshold into a bias. So here I have the expression that I showed you before, that you know, if the weighted sum of the inputs is above the threshold, then now I would like to move this 5 here on the other side of the equation. So instead of, I just want to move, you know, the 5 on the other side, and which is exactly the same. Huh? So the perceptron can be written that way instead. So here, so we will make the comparison with 0. Why with 0? Because it just makes the whole thing simpler. That's all. Okay, so now here we can start to create something. So, you know, I go and create a package, and my AI package, and here I am. So this is my package, which is empty now. Like, is the font okay? Like, can you read properly the code? Can you read my screen here? Someone can you read the code? Yes. Okay, good. Okay, very good. Okay, so let's create a class perceptron. So here, perceptron. So we say that the perceptron has some weights and a bias. And that is my class perceptron. So now we'll generate the accessors. And here I have the accessors. Yeah. So let's try to do a bit of cleaning here. So everything is a number here. You know, a number. And here we say this is some numbers, you know, some numbers. Okay, so we need now here to put that formula here in the code. So we'll create a method feed with some inputs. And then we can have something like that, inputs with weights. Then here we can have a collect. And here we have the x, and here we have the weight, and we just multiply the x by the weight. And we can even take the sum of that. Okay? And to that, we simply need to add the bias. And now here we will return, you know, we'll check that if the, you know, so in, yeah, if, so the t, this is t. If t is above, oh, let's call that z, because I use it later on. So this is z. If z is above 0, then here I will fire 1, else I just fire 0. That is good. And here temporary variable. That is my perceptron. And okay, so now I can create a class, you know, a test, you know, test case. And here my perceptron test, and here we remove that thing here. And you know, we can write some a test, you know, test basic. And here I can create a perceptron, mp perceptron. Oh, we cannot see the methods. Bigger would be, oh, how I can do that? Yeah, so a chance to increase the font like quickly? Or I can use the, like this, do you see? Was it good if I, or maybe what happens if I use the, oh, what can I do here? If I increase like something like that, is it okay? I move the code browser closer to the left. Ah, I didn't understand that. Okay. That is weird. Okay, I didn't know that. So is it okay now? You can even put it that thing a bit smaller maybe. Zoom, feed slides and look. Is that okay? Like that? Okay, so everything is okay now. You can read the code. Better. Better or good? Much better. Okay, so I can continue. Okay, now here I can create a test. So here I have my perceptron, and here I can put some weight. Let's put some weight, 1.11, and we can put also a bias. And the bias, let's pick a bias 1.5. Here I compile, boom, and I run the test, and everything is green. Yeah, okay, so there is no big deal, doesn't do much here. If the theme is a problem, I can change it, but I don't know. Okay, so I continue. I mean, it seems to be okay, I think. Okay, so now the question here, like, what can I do with the perceptron? Okay, so here I can have, okay, I can start, can have p feed. I will test the feed methods, and here let's say that if I 1, then I will multiply 1 by 1 plus 1 by 1 will be equal to 2. 2 minus 1.5 is equal to 0.5, and this is above 0. So this will be 1. Let's check. Wow, really good. Really good, really good, really good. Okay, so here I have a small perceptron with some weight and bias and a feed that works. So okay, so here this is the code that I almost have written. So what can we do with the perceptron? So the perceptron here, we can use it to express some logical gates. So here, okay, so if I have, false and false, I print that this is false. If I have true, this is false. And if I have here true, this is true. So here I just expressed some very simple logical gate. And we can do actually the same thing here with the perceptron. If I have 0.0, 0.1, and 1.0, so here this is the AND. So here I have 0, and here I have 0, here I have 0, and here I have basic AND. Yes, so I actually chosen, okay, so let's run that. That works. That is really good. Actually, I've chosen the 1, 1, and minus 1.5 here because I knew that is going to be for the AND. But we can have, so let's remove that thing here, and you can also have the OR. So the OR is almost the same thing than the AND, except here I have minus 0.5. And the OR here means that I have 1 here and 1 here. Let's check again. Oh, that works. That is great. So we have built a small perceptron, and the perceptron, actually we have configured the perceptron to be able to do some logical gates. That is great. That is great. And okay, so actually the interesting thing is when you can make the perceptron learn, because here here I had to provide it the weight and the bias. But there are plenty of cases where this is very complicated to find by hand, but what is the right weight and the bias. So here I found this 1, 1, and 0.5, by hand, by doing the equation on a piece of paper. But if you have something like more complex, where you want that your neuron to assess, to recognize some pattern in a picture, then you cannot really find by hand, which value here I need to provide. So instead, you would like the perceptron to learn. So so here, okay, so here I have the perceptron, and I can provide some input. This is what here I'm doing with this input here. And so one important way for the perceptron to learn is that you need to know like what has to be the answer. You don't know that thing here. You don't know that this is what you're looking for, but you provide that thing here and a desired output. So if you ask the perceptron to evaluate something, if you use here the feeds, and if the perceptron gives you like a wrong number, let's say that instead of here of having 1, it gives you 0, it means that the perceptron needs to learn. And the way that it can learn is the following: is that if the desired output is 0, but the actual input is above the threshold, it means that we need to decrease the weight and the bias. So here we pick a constant. In that case, this is 0.01, but it could be a different value, and the C here is calling the learning rate. In case that the desired output is 1 and the actual input is below the threshold, it means that we should increase the weight that way. So here we can write that, that method here. It's a bit long, but, okay, so here, okay, and here I have the way I can train. So here I say that, this is a method that here I will provide some input, and I will provide also a desired output. So first it will compute it will compute some, the value here, and then if the perceptron compute what you expect, then that is fine. Else here we need to do a bit of training, and the training is done like you compute. Okay, here you compute the new weight and you change the bias. Well, I mean, this is no, like no big deal. So let's use now here that method here. So here we'll do a training. Okay, training here. So I have that thing that works, that passes. So now let's modify that thing here. Let's modify with -1, and here 1.5. If I run that thing, that doesn't pass. The tests do not pass it because I've changed the weight, I've changed the bias, so there is no way that the perceptron can emulate the AND. So, however, we can do a bit of training here. We can say, 100 times I will train my perceptron that way. I will do here the perceptron. I would like to train the perceptron with those values here. I would like the output to be 0. And here I put 1, here I put 1, and here I put 1, 1, 1 here. And here I put 1. So I run that, and now here it passes. Once again, I remove that. Doesn't passes. If I put the code here, it means that the perceptron is learning. And that is great. That is really great. So I've trained 100 times the perceptron with those values. So what happens if I decrease a bit those value here, 50? Still works. And let's say like 5. Nope, that doesn't work. This is not enough training. You need to go more to the gym. So here 100 seems to go better. And yeah, okay. So let's. Okay, so this is interesting because it means that this value here seems to impact, the number of times that it gets trained. So let's put that in here. Let's put that here. So okay, so here I have my perceptron, and so here I have my perceptron. Here I do some training, and now here I will compute the error that is making. So the error here is equal to the expected output minus that thing here, and then here IBS. So here we are computing like how the perceptron is far from guessing the 0 actually. And here we'll do a plus. Oops. And here I need let's say that we like the OR behavior, and here we have the, and now here we need 1, and here we need 1, and here 1, 1. So okay, so now here we will train the perceptron. So here we have those values, and we will train the perceptron to actually simulate the OR behavior. So now here I need to do error equal error divided by 4, and let's put round 2. I do, oops, I think, yeah, sorry. Are we doing good so far? Yeah, everybody's following? So here I evaluate that thing, here I have 0, which is good. It means that if I train 100 times, then it makes no error. And if I train it like 10 times, it's making a small mistake. If I train like maybe less time, just once, then it's making more mistakes. It means that you see that here, like the value, the number of times here we are training is somehow impacting the amount of error that the perceptron is doing. So let's put that into a bit of code here. 1 to, let's say 100, correct, and here we have E, and that thing here, if I do that, I think should somehow work. Maybe that. Yes, so Yura here is asking, is the training a naive algorithm? Or I could write myself without reading a theory. Well, the training is the big deal, actually. So it is, I mean, for the perceptron here, you can guess it yourself. But as soon as we will go to the sigmoid neuron, no, you will not be able to guess it yourself. The difficult part is about the training. So here I'm making like very, very simple for you to understand, but that there is some very tough mathematics behind. But luckily, some very smart guys, smarter than me in mathematics, they provide some very nice formulas. I'm just using them now. But yeah. Okay, so here I am now doing, okay, so here I need to change the 1 by E. And I evaluate that. So here you see that you have a list of, of numbers, and at some point it goes to 0. Very good. So here are some values. Guess what we are going to do now? We are going to plot them. So here we have values, and let's use, let's say, Russell to plot that thing here. So here we have collecting the error per iteration. Exactly. So here we have graph, and we have D, a point. Then here points values, and here I say the Y is yourself, and here G adds D, and here I have G. It should work. Yeah, that works. So let's remove that thing here, D. No dots, connect color, and color, let's say blue, and boom. So here you see that the perceptron here is learning. You see the graph properly. Is that okay? So you see that here the perceptron, yeah, so the 0, 25, something here. Well, I mean, this is this is an error. This is the way that we computed the error. So this is the sum. So the error here, this is the sum on how it is simply telling you how good the perceptron is doing. So there is actually no much, what the 25 here means. Actually, you don't really care. The most important thing is what is the shape of that curve, and that is really the important thing. The shape of that curve here with the perceptron, you see that here there are some small stairs. And also, like, the important thing is that you see that the blue lines here reaches 0, which means that on some point, like after 26, the 27th iterations training, then the perceptron is able to guess accurately what would be the value of the XOR. 0.5 means, yes, I'm creating new perceptron in each iteration, which is fine, because that is fine. No problem with that. I mean, I could put that outside, but that is good that way. I am simply resetting. The important thing here that is changing with the time. That's all. Okay, so let's 1 minute. My notes. Sorry. So yeah, no, so yeah, so this is what we did that, and that is good. Okay, so here we have built a perceptron, and we have built a very easy way for the perceptron to learn. So we see that here at some point he has learned something, and that is great. So let's build a different example, a slightly more complicated example. So here I open that thing here. So instead of having here the instead of having the perceptron to guess the XOR behavior, I will just use the perceptron to identify some values from determining what is the sign of a function. So here I have a function, arbitrary function, where I have x minus 2, minus 40. And I have a random number here, random new, and here I will do seed 42. And tutuk, and here I will, for the training here, I will use x. I would say that x is a random next int, let's say 100, minus, because like that, the x could be also negative. This expression gives me a value between 0, I think between 0 and 99, and if I do that, then it will be between minus 50 and 49, something like that. So here I can say that the y is simply the application of x on f. So here I can do f value x. And then here I can have I can determine the sign of y. So I can say if y inferior to 0, then I want the perceptron to fire 1. If false, then 0 here. I could change that, doesn't really matter. And now here, I have 3 values. Now I will train the perceptron to guess this value here. So I can do it that way, and I remove that, and here I have x, and here I have y, and here I have o. Yes, this is what I have here. And now here I will compute the error. I need to compute the error differently. So here I have the error, and I will simply, so let's say that I will, so here this is the training phase, and here this is the guessing phase. And the guessing phase is the following. So here 100 times I will pick a random x. I will do that. And now here I will do error equal error plus or minus the feed x and y. And here IBS. I'm interested in the absolute value here. Okay, so I think it should somehow work. So let's do that. Oh, we see that the perceptron is somehow learning, because here we go down, but at some point it's going up. And what it means that the perceptron is forgetting. So let's maybe increase a bit the training, because, like here, let's say 400. Again, you see that it's going up and down, and, and again, what happens if you have 1000? That is good. So you see that the perceptron, is somehow like a bit erratic. Is learning, but forgetting, learning again, forgetting, learning, forgetting again. And then here, some point, he seems to really have understood the lessons, and now he can guess whether, like applying x to f, is positive or negative. That is great. That is really great. But you see that here we have those jumps here. You see those jumps. And those jumps, so I will check if there is, yeah. So you see that here I have those jumps. And actually those jumps are really a problem. So it doesn't really look like here because on some point is learning. But the thing is, like, this example is pretty easy. And if now you would like your perceptron to classify some pictures, then it may produce a wrong result. So here, like, the fact that it's going up, this is bad. This is really bad. And why on some point here is going up? The reason is that if we take the definition of the perceptron is the following. So the learning, when we train here the perceptron, what does it mean to train the perceptron? Training the perceptron means that here we will modify the weight and modify the bias. Each time the perceptron is learning, is modifying the bias and the weight. But with the current definition of the perceptron, a small change here, a small change in the weight, may produce a big change in the output. So it means that, even a tiny changes in the weight can make the perceptron to fire a different value, very different value, 0 or 1. And that is the problem. That is the reason why at some point it's forgetting. So just because here we have this small change here can produce a big change in the output can make the perceptron to forget. And that is a big problem. So yeah, so this is what here I'm showing here, that here I have those steps, and that is bad. So you remember, like, we call that Z in the code. So if now we would like to see this, we would like to plot this value here, we have that. So if so here this is this blue curve here is the weight multiplied by the input plus the bias. So if we are below 0, then the perceptron will output 0. If the input multiplied by the weight is above 0, then it will fire 1. And the problem here with that curve is that here we have some, those corners here. And those corners means that the changes are too abrupt. Mathematically speaking, it means that here you cannot compute the derivation. And the fact that here you cannot compute the derivation, it means that when you try to make the perceptron learn, then when something, passing from here to here, it goes in a very erratic way. Instead, we will change that blue curve here. Instead of having that blue curve, which has some corner here, we will use a different curve that doesn't have any corner. So here we have that blue curve here, which is smooth. Like it gives the the feeling to touch it, right? I mean, you will not pick your finger. So here there is no abrupt changes. And the important thing here, the important aspect of that curve here, it means that a small change here horizontally will produce a small change vertically, even in those cases here. So the equation behind that curve is that one. So that is the equation behind that curve. And so we will write it now here. So we will now, okay, so here this is the class perceptron. So I will create a new class called neuron, which is a subclass of perceptron. So here I have MP neuron. And here I remove that. So here I have my class neuron. So here I will just copy the bias. No, the feed method. So here I have the feed methods. And then I will change that because I'm not happy with those big changes here that could happen. So instead I will just copy that thing. So here this is 1 divided by 1 plus zeta negated exponential. Really good. So here we have the NP neuron. So let's go back here to that thing. So now we will change the perceptron with the neuron here. I run that script. Not quite right. You see that you have all these small, up and down. And the reason is that the training is not good. The training here we have done is the way that we train a perceptron can be used for the training neuron. So here we need to have a different training method. So let's have that thing here. And let's run again. So now here we have different training methods. Okay, so let's... I did something wrong, no? Oh, let's increase that maybe. 3000. It should have learned at some point. But it could be that... Oh, there is something weird in the way that I'm doing. And why here the perceptron is not, the neuron is not learning? If I do like phase 5 here, no, it's not multiplied. Nothing here. Oh, what happens? Sorry, that's a bug. I don't really know why here is not. And if I change that here, the MP neuron, yeah, it's somewhere learning. So here there is something wrong in my script. I cannot immediately figure out why. What? Maybe that thing here. Yeah, so somehow here that thing makes the whole, yeah, so changes a bit. But anyway, so that's the idea. So now here we have like the perceptron. So here, I will remove that. Let's say 1000 should be enough. So okay, so here you see that the neuron is learning like much better than perceptron. Let's change that again for the perceptron. Ah, something wrong. Oh yeah. Ah, here I forgot the ABS. No, here it is the ABS. And here I have a neuron. And if I have here minus 0.5, could be that the bias is too high. Okay, and here I have the perceptron. Yeah, okay, so here MP neuron. Okay, so anyway, here I have like the a neuron that has okay, so here a better way like to learn. So the example is too small, it's so small that it is maybe not that obvious, but here this is what happens, is that we change the way that the neuron can learn. And this is done by here having this, so here we compute the error, which is the difference between the desired output and the actual output. And then here we compute the delta, and that thing here actually is something that you cannot easily guess. So that thing here is actually the derivative of the sigmoid function that I mentioned before. And then here we are updating the weight with the learning rate, with the delta and the input, and we are doing the same thing for the bias. Okay, so this is exactly like how the learning, how it works for a neuron. It's really good. Okay, so now here we might move along. So let's reuse that thing here. So I will remove that here. So this code here was about like the perceptron learning the XOR, not the OR logical gate. We have that, and we can change that for the neuron, MP neuron. You see that here now is smooth. It goes, slower, but it's smooth. And here I can change that to 1000, and boom, here, ultimately it goes down. So, we see that we can make the perceptron, the neuron learns the AND, the OR, but let's try with the XOR. The XOR is that thing here where I have 0 XOR 0 equals 0. 0 XOR 1 equals 1. 1 XOR 0 equals 1. And 1 XOR 1 equals 0. You know, that thing here. So let's see how it goes. We see that no, it doesn't really work. It doesn't learn, and you can increase that the way you want. It doesn't learn. So it means that. So it means that somehow the XOR logical gate has something special at the end, or the OR gate doesn't have. So the XOR logical gate is somehow more complex for the neuron, and the neuron is not able to learn it. And so this is one reason why we need something else than a simple neuron, and we need to connect a group of neurons in order to make that. We need to connect a group of neurons to solve some more complicated problems, such as the XOR or recognizing a picture. And okay, so here this is what a neural network looks like. So here we have some, we have some input, we have some layers, and we have one output. So we have 4 layers, and in that case here we have the output layer. The output layer is the one that we produce the values. So on this example here, and the one we will use, we will just have one output. But we could have like many outputs here. You know, it could have actually more output than inputs. You know, it could have like as many output you want. And here we have the input layer. Actually, this is not really a layer. This is not, there is nothing special. It's just providing the values here to the hidden layer. And we here have hidden layer. We have 2 hidden layers. We could have like 1 hidden layer, we could have like more than 2 hidden layers. And we have that, amount of neurons. There is not really a rule on which, what is the amount of hidden layer, we need, and how many neurons we actually need. No, there is no general rule on that. But now, like, let's use so here I will use the class neural network, and this is why actually here I need a package at the very beginning to have the class neural network. So neural network here will have 2 inputs. We'll have 1 hidden layer and with 2 outputs, and we'll have 1 output. Now here so here we need to put that into an array. And I think that's all. If I do that, right here I need to do first, because the feed here can provide a set of output. So we just need the first output. I'm training that now here. It takes a bit longer. There is something wrong. Okay, so here I have 1000. But actually, like 1000 is not enough. Let's say here by 250 maybe. So here we are using the neural networks to learn the XOR logical gate. And we see that boom is going down here. So the neural network is able to learn something as complex as the XOR logical gate. Okay, so so here there were some. There were like such summary formula. So is the formula correct? Maybe minus is missing. I do not see X in the code. So tuk. Sorry, I didn't see the. So here the feed. See here there is exp. No, if this is what we meant, arrow doesn't calculate ABS. Yeah, it doesn't really matter. I mean, this is. So what is the set of output? So here in that case, it will be 0 or 1. Actually, it's not really 0 or 1, but a value close to 0 or close to 1. So here you have the neural network. I can inspect it, and you have some nice things here. Oh, something got frozen. Okay, so here we use the neural networks to make prediction on what the output of the XOR logical gate could be. And that is really, that's all. So something here, okay, so and that is really like the way that this whole thing works. So here we have a small neural network that can do something very simple, but we can use exactly the same neural networks to classify some data or doing some picture recognition. So let's use here a small example. So we use a canonical examples for in image classification, in data classification. So here, so this is some flowers. And this is called an iris. An iris is beautiful. And there are three kinds of iris, I think, in North America, somehow. And so here we have the versicolor, and we have the setosa, and here we have the virginica. So we will use a data set. So in we'll use a data set that got the result of someone one day that took 150 different flowers and started to measure like the size of the petals, the width of the petals, and doing some some measurement on the flower. So here this is like a very famous data set that was made in the 80s, Iris Plants data set. So I think that, here we have, so here we have the sepal and the petal, and you have, some attributes. And okay, so here there is a bit of description of the, so the data set is actually here, so you can just use it. I will show it. So the data set is, so if you have downloaded like the neural networks package, then you should have that thing here. You should have that thing. So this is what I have, So here I have that data set. This is what I have here. So here, this corresponds to some attributes of the flower, and here the class of the flower, the name of the flower here. And so here there is 1, 2, 3, 4 attributes. So I can have the second here, or I can have like the fourth. You can have the thing here. And actually, like if you want to understand a bit more like this data set, then we can use the Russell visualization that we have made, which is that one here. So this is like a very nice visualization we built in Russell. So you see like a comparison of all the different dimensions. You can even select one thing here, I can move that thing here. It's pretty, right? Don't you think? Yeah, so here, we will do some machine learning. We'll use the neural networks to make the classification of that data set here. So here. So here we have the data set, that thing here. So this data set here is actually exactly the same than previous. I can. Okay, so here I have this data set, the original data set. So here I've changed slightly. So I will use in the neural network a slightly different version of this data set. The reason is that we just replaced the name of the flower here by a number. Because the thing is, the neural network just deal with numbers, but here I have a string, so I need to convert that string into a number somehow. And this is what I'm doing. So here I have a new version of the data set, where here I have some numbers at the last column. And okay, so here I mixed the lines, and then here I will cut the data in two. I will use a training set that corresponds to the first 80% of the data. So here I have from the 150 data here lines, I will just pick 120, and I will train the neural network with these 120 items. And here I will, the remaining one, the 30 remaining one, I will simply use that as a guessing. So here we create a neural network. The neural networks, I will configure it with 4 inputs. one hidden layer of 5 output, no, 5 neurons. So I have the neural network with 4 inputs. I have 5 neurons in the middle layer, and then I will have 3 outputs. The 3 output is because this is just the neural network just will fire one to the neuron that correspond to the class of the flower. So I have 3 flowers. So behind the 3 flowers there is one neuron, and we just pick one that correspond. So here I will do. Oops. So here I will do the training. I will. Okay. So here. Okay. So here I will do the training. So I'm training the neural networks with this data set here. It's done. Now here I can compute the precision. Let's compute precision. Boom. I have a precision of 90. So I have 90% precision. Okay, so I have 90. No, sorry, there was something wrong before I did, because I'm evaluating line by line, so somehow I mess up. But the thing is, the neural network was able to predict like quite accurately this guessing data set here. So here I'm, for all the guessing data set, I'm doing a prediction. So here is a method that I've defined on neural networks. We can see it, but it doesn't do much. It's just like feeding the input and checking like which outputs, telling numbers on, yeah. It's just some small utility methods. And here I'm checking like the number of lines that were correctly predicted using the neural networks, and I'm just dividing that by the number of guessing data here I have. And this very simple thing here gives me a precision of 96%. Let's try to increase that. Let's try here to have the 90%. So 90% of the data set will be about like the training. Yeah, actually we see that here is decreasing because we are doing something which is called overfitting. We are training too much, and then at the end is not able. So let's decrease that. Let's 50%. And we are decreasing a bit. So what happens if instead of here, so here I have a mixing. So what happens if we remove the mixing here? And let's again evaluate that thing. And now here the precision are reduced a lot. And the reason is that, the reason is that 50%, it means that of 150 minutes, here we have 75. So we have trained the neural network with data just above that thing here. But it means that just with one as the class to be guessed. And it means that the one with 2 that doesn't know it, so it will get it wrong all the time, because at that time like the neural network doesn't know about the 3rd class, so it cannot make any good prediction on that. But yeah, so this is like a brief introduction of neural networks made in Pharo. So something which is missing here is that we didn't show how to train the neural network. Actually, the training of the neural network is where it is really complicated. Well, I mean, really complicated. It involves a lot of mathematics. So, but it's done, and actually here I've used it like to show how can we use the neural networks to classify some simple data. But this is really how the idea works. So now here you can use exactly the same neural networks and classify some pictures, and that works well. That works really well. But it all depends on the kind of pictures. But some simple picture that really, for example, like if you have some hand-digit written numbers, then the neural networks is able to make some very good prediction. Okay, so I think that's all. This is all what I want to say. So if you have any question, I will be really happy to answer. So I hope it was clear. Yeah, so question, just please ask. so at that point the talk is over. So now I'm just waiting for some questions. So if there are no questions, then well. Okay, so here someone is asking, Dennis is asking, like, so training was on meta information of images and not binary. Okay, so here the training is on the meta information and not binary data. Well, I mean, you can do the training like the way you want. I mean, there is nothing there is nothing hidden here. So the input of the neural network is a set of numbers, and those numbers could be anything. You know, it could be like just the intensity of a pixel. You know, like 0 is black and white, and 1 is white. Or it could be like some Fourier coefficient that you can use. You know, it could be on anything. So it actually could be like on any kind of data, really, literally any kind of data. And that is really the magic behind neural networks. So you can really use the same piece of code to classify the XOR logical gate or to really classify pictures, more or less. This is really how it works. So how you can define the neural network structure? So neural networks is the class here that's okay. So here this is a class, this is a small package that I've defined, and you can say the number of inputs you want to have, the number of hidden. You can have like more than one hidden layer. So here configuration, you can have like two layers, 1 layers, 3 layers. You can have more, but the thing is, at the end, a neural network with many hidden layers is very hard to train. It's really, really hard to train. So here there is no silver bullet. More hidden layer you have, and more complicated it is to train. But that's all. This is how you define it. And at the end, this is really easy. So a layer is a collection of neurons, where here I have the weight. In that case here, I simply use some random number for the weight and for the bias here. I think if I do that, new numbers here, random next. So I think this should answer the question. I think here I can do something like, I can do inspect here, and yeah, so here this is the error. So, okay, so here, so I just inspected like the neural network, and here I see that I have a curve that indicates the error that is making, the neural network is making here. And so here this is the configuration of the neuron here. You see that you have 3 outputs and we have 4 inputs. Actually, I do not represent here the input, but I have 8 neurons as a hidden layer. Actually, yes. So if you need to have like less layer and more neurons in one layer, yes. So, but actually it depends. So there is not really a clear answer to that. So you can have, so there is no magic rule that's saying how many hidden layers you need to have. Having 1 hidden layer is good. Having 2 hidden layers is better. Often it is often better, but they have more neurons also is quite good. So if you take like the neural networks that Google is using to classify some text, there are 2 hidden layers only. So there are plenty of neurons, but they're not mean that hidden layers. So yes, it is better to have few hidden layers and more neurons. So performance is, well, I mean, you have seen, right? I mean, you have seen that how I classify some text, some values, and well, I mean, that works reasonably well. So the implementation here, it doesn't do any optimization at all. So one of the first optimization you could have is instead of having here this, like I have the object neuron, but the thing is like one way to improve the performance is to replace a layer by actually a matrix, and this is what most of the professional machine learning tools that will do. They will have here a matrix, and not really because the matrix is more efficient than the object. It's more because the matrix goes well on the GPU. So then you can put the neural networks on a GPU, and that really works well. And there is nothing that prevents us from doing that in Pharo. Yeah, so if you randomly swap the training data, you could improve the precision. Yes, so it's better to have a very well shuffled input. That is true. That is true. It's better to have a well shuffled input. Yes, and increasing the data size is the data set is the way to improve the accuracy of. I mean, there are several ways you can improve the accuracy, but the best way is to augment the number of data that you have. More data you have, better it is, more accurate it's going to be. But in many situations, like a very simple way, you have your data set, you take 80% and 20%, that works well. I tried, okay, so then Pavel is asking, like, I try to find how learning works in biological networks where you have no given correction mechanism. Once I heard that the neurons improve link between neurons that fire together. Do you know about some types of artificial networks based on that? Yes, actually, yes. So this is like important things. So something so okay, so we talk about how a perceptron can learn. We also talk about how a neuron can learn, but we didn't really talk about how the neural networks can learn. The learning phase is really, I mean, this is like pure mathematics. So there are some, so you use a mechanism called backpropagation. There are some different mechanisms for training for training a neural network. So Pavel, what here is asking, like, can we have a neural network without this learning algorithm? Yes, we can. Yes, we can. So maybe like a different tech talk, I can talk about genetic algorithm. So genetic algorithm is a mechanism that finds the best solution for given problems. And we can combine the neural networks with a genetic algorithm. In that case, we not need this complex algorithm to train the neural network. And actually, like this is like something which is really interesting in many cases. For example, here I use the training data to make prediction. But it could be that I don't have any training data. Consider now that here you have a game. You want to create the artificial intelligence of a player in a game, in a video game. There is not but the best way to play a game. Well, there is not such a thing. You don't have a data set that tells you, like, what is the best movement of my hero here. There is no such a thing. And often what happens is that, or either you are Blizzard and you have like millions of users and you can record that everything and find what is the best game, or you can use a smarter thing such as using a genetic algorithm. And then in that case, you will try to improve the neural networks, not based on some examples, some training data, but more on identifying which weights and which bias will increase the accuracy. So what does it mean, and what does overteaching actually means? Well, I mean, there's no really rule on when do you train too much neural networks. So if you train too much neural networks, you have something I call overfitting. It means that the neural networks will be really good at exactly the same data set you have provided. If you go a bit off, one of the data, boom, it will do bad. So this is something that happens when you try to improve it like too much. Not to improve it, but when you try to make it learn too much exactly the same thing. It'll be like human, right? You're learning always the same, reading always the same book doesn't make you able to read other book, right? So any other question? I see that someone is typing here. No, so if there is no other question, then I think that the talk is well. I mean, I think that's all for today. So yeah, so thank you very much for the participants. Thank you very much for the your encouragement. Many people ask me like to do this talk, and thank you very much for to Marcus and Karen. Thank you very much for the AirMod team, and thank you very much really to all you guys. So the code here I provided is not really like ready for public consumption. So documentation will come. It will come, that for sure. But currently it's not. You can use it, but at your own risk. I mean. It's not. I mean, I used it as a support for a lecture, and not really as a product that anyone can use. So it will come at some point, but just is maybe not ready yet. So, and I also like, if some of you guys have some needs about have some needs about applying neural networks for any kind of program, then I would be really happy to help you. Really happy to help you. So my final words on that is that I do think that in Pharo we can do some great machine learning techniques, really. But as soon as we are not doing images or text processing, neural networks in Pharo really works well. So yeah, so guys, see you, bye.